called Ring, which is our key value store that allows users to change storage scheme of key value pairs without compromising efficiency and consistency. The problem of storing data reliably is a well-established problem, and in response to a variety of application requirements, many storage schemes have been developed. The most popular one is replication, when the client sends its data to key value store where it's replicated or like multiple copies are made. And like replication, in erasure codes, no additional copies made, and key value store generates special parity updates which are propagated to the parity nodes. So in this work we focus on read-Solomon codes, and you're probably familiar with them from RAID 5 and RAID 6 storage systems. And finally, in memory, key value store can be used as a caching layer, for example, for caching query results where no redundancy is present. So different storage schemes, they have different advantages and disadvantages. Replication is a simple scheme which provides a decent level of reliability and availability. However, it has really high storage overhead. On the other hand, read-Solomon codes, they provide the lowest possible storage overhead, but it involves computation to generate, update, and recover data. And finally, caching is the fastest way to store your data since there is no redundancy. However, it's not fault tolerant. And what is more, different storage schemes, they provide different trade-offs in utilization, in reliability, availability, performance, and utilization of cluster resources such as memory, memory usage, network load, and CPU load. Here you can see comparison between caching, where is no redundancy, replication-free when we have overall free data copies, and read-Solomon free too, when we have free data nodes and 2 parity nodes. The problem of, or weakness of existing key value stores, that they support only one such storage scheme, and as a result, companies maintain dozens of distinct key value stores, which has to be maintained separately, and they could even have different APIs. And it increases complexity of deployment of the system. So, and also it's not even clear how you can move the objects across the key value store and be atomic. So clearly there is a need in a key value store which can support multiple storage schemes, but now I'd like to introduce use cases of such key value store. First of all, the potence of the data can change over time by intrinsic nature of the data. So we have, for example, we can have temporal computations, and they shouldn't be stored redundantly. And when we've finished our computation, then we would like to store them durably. Then we could make additional copies, for example. Or, for example, in Snapchat, when you upload your picture, they have to be stored reliably only during the first day of your, after the first day once you upload your data, and then the redundancy or the reliability requirements of your data can decrease since your picture will vanish anyway soon. So I'd like to point out requirements the key value store has to comply with in order to enable such use case. First of all, user has to be able to change storage scheme at key granularity, and also user shouldn't know how data is stored in order to access it, so it has to know only the key of the object. The second use case is multi-temperature data management. Quite often in data stores we can distinguish between hot and cool data depending on the access frequency. So cool data is less frequently accessed, and to optimize utilization of cluster resources, it's usually stored with read-Solomon scheme. So to enable this use case, we need to support both replication and erasure coding, and plus the changes of the storage scheme, they have to be immediately visible to all other clients. Finally, there have been many work on relaxing consistency to tune performance. Here we proposing tune performance through changing storage schemes. And to enable this case, the process of changing storage scheme has to be cheap, and it has to be consistent. So our key value store complies with all these requirements, and it supports the following API. Here we have conventional function like get, put, and delete when the client is oblivious to how data is stored, or he can client can specify how he wants to store the data with specifying the ID of the storage schemes. And with create call, client can assign a storage scheme to create storage scheme and assign it to some ID. For example, client can create replication 3 and assign it to ID 0, and then use this ID when he writes data to the key value store. And also he can change on the fly the current storage scheme with a move request when he can specify only the key of the object and the desired storage scheme. So I can talk a lot about all challenges. Now I'd like to focus on the solution. The key to achieving high performance is to reduce communication overhead, so we chose decentralized architecture where we have assigned key shards to the physical nodes, and the client applies a hash function to the key and then directs its request to the required machine. And the key idea here is that we stack together different storage schemes which share the same key to node mapping. So here we call this storage scheme mapjust, and in this example they all have the same number of key shards, which is equal to 3, or they actually have the same key mapping. So since on every physical machine we have all storage scheme, this request can be directed locally further to the required or requested storage scheme. The problem here that not all storage scheme can have the same number of key shards. And the problem comes from read-cell-1 scheme. In read-cell-1 scheme, the number of key shards or number of data node is actually strictly connected to the encoding. So to circumvent this limitation, we designed our modification to read-cell-1, which we called stretch read-cell-1, and I'd like to introduce it on the next slide. So here we can see read-cell-1 to 1. We have two data nodes, one parity node, and the data on the parity node is equal to XORing data on the node 1 and node 2. So in other words, D1 plus D2 is equal to P1. And here we have two data nodes, the two primary nodes which can be accessed, so we have only 2 key shards. And if we'd like to have three key shards, as in the previous example, we need to do something. And what we are proposing, first, we need to split our data. It doesn't change, encoding can just change the granularity of the updates or granularity of coding, but the data stored will be exactly the same. And then we actually distribute these blocks over as many machines as we want. In this case, it's 3. So every machine will get 2 blocks instead of 3. And the key idea here is to preserve the coding scheme. By preserving coding scheme, we inherit all properties of original read-cell-1. So stretch modification will have exactly the same properties as the original one, and the only concern is reliability. Since we increase the number of machines, and then in this case, since we increase the number of machines, the probability of single failure has to increase. And we'd like to study how it influences reliability. So we performed reliability analysis based on continuous time Markov chain model, and here you can see reliability of read-cell-1 to 1. It has reliability a little bit less than 4 nines, and it has 2 shards. And we right now can stretch it over 3 machines, 4, 5, 6, 7. As we can see, the reliability didn't change much, and sometimes it goes down or goes up, but it actually stays the same. We performed the same analysis for different read-cell-1 schemes, and we showed that in all cases we studied, the reliability hasn't been changed dramatically. And also you can see a small artifact here, for example, read-cell-1 3.2. When we stretch it over 6 machines, it even increases reliability, and we describe this artifact in the paper, so have a look. Now I'd like to have a closer look at the architecture. Here we have 5 machines where the 3 machines, their primary one, we assign 3 shards to them, and the 2 machines at the bottom, we call them redundant one. They use just for storing replicas or partitions. So when user asks to add read-cell-1 to 1, we said we have 3 key shards and we have to use stretch modification. So we add stretch read-cell-1 to 1, 3. Then the user could ask to add read-cell-1 3.2, we can easily add it, or then user can ask to add storage scheme with no redundancy, we call it replication 1, since there is only one copy of the data, and number 3 stays for the number of shards. When the client asks to add replication scheme, we partition the replication scheme into 3 shards and make replicas for each shard. And the same way we can do for replication 5. So the key idea here that all the storage schemes, they have the same key to node mapping, and the key will be assigned to unique physical node. So on the physical node, we have multiple different storage primaries of all storage schemes, and in this case, there will be only one coordinator of this particular key, and we can easily change the storage scheme. So if we'd like to change this, and we resolve problem with consistency by using versioning. Basically, when we change the data or move update the storage scheme, we just increment the version, and the client will always access the latest version of the key. So now I'd like to move to evaluations. We done all our tests on our 12-node InfiniBand cluster. Current implementation use RDMA, and it's single-threaded. For array codes, we used ZeroSure library, quite famous open source library, and all tests we did with 7 different storage schemes, which we call MapJust, and with 3 key shards. Here I'd like to focus on the main result. Other evaluation you can find in the paper. Here you can see the put latency for 4 different MapJust. When replication 1, it's no redundancy, replication 2, replication 4, and straight read Solomon 3.2. So as we can see that all these schemes, as we said, they have completely different trade-offs in terms of latency, but now I'd like it compared to the move request which we introduced. As we remember, to move the data, we just need the key and specify the storage scheme. So on the right part of the slide, you can see the latency of the move request. As we can see, for the smaller sizes, we have additional overhead. It comes from the fact that we have to resolve versioning, but later the latency it's actually reduces. And the reason for this is that when the client sends move request, he doesn't send the data to the key value store because it's already had it. That's why it pays off more when you have larger objects. In the paper, you could find more evaluation when we compare our key value store with other systems, but it's not the main idea of our key value store. We're not trying to compete in performance with our key value store. What we want to show that actually you could support multiple storage schemes at low cost and without compromising API or consistency or efficiency. So to conclude, we design. To our knowledge, this is the first key value store which allows user to change storage scheme on the fly at low cost. And for this, we had smart allocation of our storage scheme and the key shards. And for this, we designed a straight read Solomon scheme to have an arbitrary number of shards for read Solomon schemes. Thank you for your attention. Any questions?
Yeah, let's thank the speaker. So we have time for questions. So while you're all thinking about the question that you want to ask, let me start by asking about your API. So you have this key-centric API that gives you a lot of flexibility, but what about bulk updates? So if I want to, change my storage policy affecting all of my keys or a large group of my keys?
Unfortunately, we haven't implemented it. It's possible, but I think it would be difficult to enforce strong consistency. In that case, when you have multiple updates, then you need something like transactions. It would be more challenging.
So do you think in practice you would require efficient support for these kinds of bulk updates, or could you get away without having it and then not having to worry about a strong consistency?
I cannot think about application, but for example, Redis, it supports like bulk update, but you never have this fine granularity for each key. And I think for many applications, it's more important to have it per key rather than per the range of keys.
Okay. So any other questions?
Yeah. If you have other questions, we can discuss it also offline after the conference. I will be happy to discuss other details of the paper.
There's one question there.
Hello, really good talk. So I would like to ask what kind of strong consistency do you support? Is it per-key sequential consistency or linearizability, or how do you define
Linearizability.
linearizability? So you invalidate all of the. So do you have a primary, or how do you guarantee such a thing?
Since we have one coordinator of the key,
Okay.
this node is responsible for everything.
Okay, thank you.